I'm going to talk about the long-term performance of asphalt rubber mixes. As he mentioned, I spent almost 20 years with Caltrans. I started a lot of the research and development of asphalt rubber. The first project was in 1983 that I showed up on, and it happened to be probably one of the most documented ones statewide. I think you've seen this picture many times, but this core is still sitting in our Phoenix office, still intact. It just shows you how amazing the product is on a 25 millimeter overlay, and you can pick that up and it doesn't fall apart. It's just a really unique material. And if you look there, you can see that there appears to be a crack on both sides where the crack has reflected up through. A lot of times that's what you see in rubber. It looks like there's a crack there, and in your mind you think that crack goes all the way through the pavement. That's why the material heals up, is because as traffic runs over it, it warms up, that crack goes away. That's why a lot of times you'll hear people say, well, the rubber mix is cracked up when they look at it in the wintertime, but they'll come back in the summertime to show you where the crack is and they can't find it. So, I mean, it does heal itself. The history is now approaching 40 years of the product. So it's something that's been around a long time, been researched to death, but there's still a lot more we have to learn about the product. It's amazing to me that there are folks today that still consider asphalt rubber in the experimental phase after almost 40 years of history. This is what crumb rubber looks like, and I'm sure you've seen it before. In all the years I researched products that when I was with Caltrans and after Caltrans, I've never seen a product that can perform like asphalt rubber. You know, the key is the crumb rubber in there, and the key is the extremely high viscosity and strength, durability, and oxidation resistance of the product. I want to briefly just show you how in the early years we learned a lot about the product in what I consider one of the most important studies done in the middle 1980s. And one of the things, you got the, okay. I want to show you this is one of the most important slides, I think, and what it is viscosity on the vertical scale, and the horizontal scale is the percent crumb rubber. And if you follow this line, what you see is as you get up around 10%, there's a very slow slope, and as you get up to 15%, it even gets steeper. But look what happens around 18%. This is where we are, and that's why the product performs as well as it does. It's got an extremely high change, large change in the viscosity of that original binder. That's why you can put so much binder in the mixes. It has a very high shear resistance. It performs very well in the field. These slides, basically, I'm just going to show you, just give you an indication of changes in the different types of properties that we look at in binders. This one here is the viscosity versus the temperature. And basically what it shows you is that at the same temperature, you can see the very large change in viscosity of the product. Over here, we see the temperature susceptibility of the material. In all of these, the blue line is the rubber. Now, what this is important is an ideal binder would have a horizontal line. That means it would perform the same in cold climate as cold climate as it would in hot climate. Unfortunately, we don't have a binder like that. But some might look at this and say that that's not a very great change, but when we look at the temperature susceptibility of asphalts, this is very important. Even this is a log-log scale, so that's a very great change there. Here we see the different changes that we have in the tensile stress versus temperature. And what this tells you is what happens at cold temperatures. You can see that there's roughly a 10-degree difference in the property here. And what that means is that in cold climates, rubber is going to perform a little better, or quite a bit better, when you look at the 10-degree change that you get between asphalt rubber and the conventional binder. Over here we have softening point. Again, these are big changes when you look at how the material behaves in the field. The softening point tells you that in hot climates it's going to stay stiffer rather than becoming fluid. Down here we have the repeated load creep test, and basically what this is showing you is the ability to resist rutting. And if you had a horizontal line here, that would mean that there is very little change in the material as far as resistance to rutting. You can see that the red line, it starts to go up at a pretty steep slope, indicating that the material would creep or it would rut in a period of time. But this is why asphalt rubber has a very high stability value, theoretical stability value, as opposed to what the number you get when you run the stability test. Because a lot of the tests that we have, because this is such a resilient material, it gives you a number that is really different than you get with conventional mixes. The last thing here is in aging, and there's two different ways that this was measured. In the thin film oven test, which is in the laboratory, and then an 8-day weatherometer, where they vary the temperature and they measure the difference in properties. And you can see that there is a difference with these, indicating that asphalt rubber has a higher resistance to aging than conventional mix. Now, these tests were done, like I said, in the 80s, and this really opened up the eyes of a lot of folks that, from the 60s to the 80s on why this material performed well in the field, because the laboratory tests were indicative of performance in the field. There's been a lot of use, and this has been talked about before, as far as who's been using a lot of this material. California, Arizona are really the two big leaders. I think probably in the very near future, California will probably use even more than Florida when it comes to the amount of chrome rubber. What type of strategies have we used with asphalt rubber? We've used hot mix, dense, gap, and open graded. We've used them in chip seals, cape seals, and multi-layer systems. And really, the last one on this list, multi-layer systems, is what I really consider just an unbelievable product, combination that you'll see why towards the end of the presentation. Here we see you can either have a one-layer system, which is strictly just an overlay or a chip seal. You could use the chip seal as a SAMI, as an inner layer in here over a cracked pavement, then put something on the top like an asphalt rubber mix. Or we could go further to a three-layer system where we have a leveling course to level up the ground, put the chip seal, and then an overlay. These systems, as I'll show you later, can be very, very cost-effective. This is basically the multi-layer systems is what my paper was presented at the conference here, which will be done later today. How was it first used in California? Well, up in the snow country, we had a real problem with our concrete pavements. They had got to their design life. They were beginning to polish. As you can see in the foreground here, they were cracked. A lot of chain wear up here, buses and trucks. This is a major thoroughfare, I-80, between Sacramento and Reno. It's an interstate, and it was beat up, really beat up. So we said, well, let's try some of this, quote, new rubber stuff and put it up on some of these roads and see how it performs. So we did an evaluation early on, and it's interesting to me that there's a lot of folks today that think that you can't use chrome rubber binders in dense graded mixes. You've seen that a number of times in the conference. I find that ironic because all of the early projects that we had and had great success with were all dense graded projects. These were the projects, the original 31 that we looked at, and almost every one of these was dense graded material. You can see we started out in the snow country. It performed so well there, we began to move to the valley, to the coastal, and even to the desert. Wide range of usage. We looked into the dry process, but we had very poor success with the dry process. This is after just a couple of years over a concrete pavement. We had got extensive cracking and potholing. We had areas that raveled very badly. We had areas that rutted, that potholed. This caused us to move away from the dry process and strictly look at the wet process by Caltrans. So where has it been used successfully? Well, it's been used successfully just about everywhere. I could show you many, many projects at all different ages, but I'll just give you a little flavor of some of the projects and the type of things we did. This was a bridge deck up by Redding over Shasta, and there was actually two bridge decks placed, a very thin overlay on the deck. There was a problem with the underlying system that was placed. It had a lot of different twists to it for a bridge deck, and they had problems with it, so they put rubber on it. Unfortunately, the rubber, because of the underlying material, the rubber only lasted about 5-6 years at this location, but it did alleviate that problem for at least 5 or 6 years. This job is one of the oldest jobs I'm aware of. This was a dense graded project placed on I-80, and it was 21 years old when they rehabbed it 2 years ago. 21-year-old dense graded rubberized asphalt concrete. Had very, very little maintenance on it. I think the first maintenance on it wasn't until like 15 years before they really did anything. So it performed very, very well. It's also ironic that there are statements made today that you can't place asphalt concrete projects up in this environment and have them perform because of the traffic. And this is probably the same length as a concrete pavement when you look at 21-year design life. This project was placed in the desert, and it was a 5-year warranty project and is still performing today, well past, I think it's somewhere in the neighborhood of 15 years old. But it was in the desert, very hot area down by Salton Sea. This was an interstate project in the Bay Area, performed very, very well. It's showing you the interstate type places that we've placed it, that it's been used. This here is a 21-year-old chip seal placed in Arizona, Indian School Road, still performing after that date. I'm not sure when they finally rehabbed that or overlaid it, but this picture was taken at 21 years. And all chip seals will not last 21 years, but it gives you an idea on some of these projects that how long they did last when they were left alone. This project was really unique in that all the Star Wars movies were shot out in these dunes, which were down off of Interstate 78 near Glamis. The pavement was first cold-in-place recycled. Then they placed a 2/10 asphalt rubber gap-gated mix over the top. They left that there for 4 years. They came back with an asphalt rubber chip seal on the top of it as a pavement preservation technique. I would say that this is a very, very outstanding and economical way of handling the traffic on a project like this. So it was kind of unique. So how did we get to where we are today? Well, this was probably the project that I referred to earlier, that one of the first projects I walked out on that was rubber. And it was known as the Ravendale Project. And what we did on this project, it was up in the high desert. It did not have a lot of traffic on it, but it did get some chain, with about 20, I think it's somewhere around 20 chain days a year. And it was built in 1983. Now, what we did on this job is, when we designed this, we placed different thicknesses of rubber. This is a SAMI. There's no SAMI here on the 45 millimeters. The same thing was used with the dry process. But what we did with the conventional is we placed different thicknesses all the way up to the design thickness with conventional mixes. So the idea is in a very short period of time, the project was first set up for 4 years. I had to extend the project 4 times. And we also put some chip seals and double chip seals. This was the design overlay thickness, 6 inches or 150 millimeters. This had some of the highest deflections that I had seen in my entire career. There was only one other job that I saw that had deflections well above this. But we wanted to put this down. The idea is when these failed, we could compare it to one of the thicknesses and find out how well it was going to perform. Well, in the first year, the thin sections all failed. This picture was taken after 2 years. It's got a chip seal that has been placed on it, and you can see it's been crack sealed. 2 years old. And this was typical of all of the thinner sections other than the overlay of 6 inches or 150 millimeters. In the first 5 years, the only crack that showed up in the wet process rubber mix was this crack that was over a culvert that was underneath here. So you can see why I had to extend the project. There were no cracks in any of the other sections. That was the only crack that showed up. This is all well documented in a number of reports. The district went out every year at the same locations and had a big boom and took pictures of the pavement and documented that over a 12-year period. These are the rubber mixes. You can see here at the beginning of the job. After 16 years, this is the 45 millimeter over the SAMI. You can see there are a few cracks here, but that's a pretty good looking pavement after 16 years with only 45 hundredths over a SAMI. Another shot showing you there is a little bit of raveling, but there really was no alligator cracking here. Down on this portion of this section, which was the first 2 sections here, there was some cracking and distress that showed up earlier, but it lasted 10 years before they had to go in and put a blanket on it. The reason is that this is a lower area down here, and it's very wet, and there's a lot of movement. But it performed the 10-year design life that you would look at for Caltrans. You can see how some of the cracks, and this is very typical of rubber. Anywhere there's traffic, you'll see that the cracks just disappear. You run traffic over that, and it just needs that crack together. Now, this is the section that's 75 millimeters over SAMI after 16 years. There was zero maintenance on this section in 16 years. Absolutely no maintenance whatsoever. And you can see why. This picture right here shows the rubber section that I'm referring to. In the foreground is the rehab they did, and this rehab is at I think it's around 6 or 7 years old at this point. I'm talking about the rehab, whereas this was 16 years old. These sections on both ends of the last two sections that were there the pavement was getting so bad they had to rehab it, so they overlaid those sections. But you can see that after 16 years, that's why we got very excited about reduced thickness asphalt rubber mixes. So in 1992, we came up with the reduced thickness design guide based on performance in the field. We started to reduce all the projects from 1986 on. It only took 3 years for us to determine that we could reduce thicknesses and get the same design life. We did work with SAMIs, and this asphalt rubber chip seals used as a SAMI is an outstanding product, and I'll show you why a little bit later. So in 1992, we came up with a reduced thickness design guide. It was based on laboratory work and a lot of work in the field, actual field performance data. And again, you've heard this earlier that Caltrans uses a deflection-based design, and we did this project in conjunction with CSIR, which is the Council on Scientific and Industrial Research in South Africa, and we also had work done at University of California at Berkeley. It was a very interesting project because we utilized the heavy vehicle simulator. After this project was over, Caltrans actually purchased 2 of these, and I'm going to show you what we used them for here. This is a heavy vehicle simulator, and it's a machine that can move under its own volition because it's got an engine in here, but it'll only drive from test section to test section. You wouldn't drive it for long distances. But it has a beam in here, and a wheel runs back and forth. Here you see the picture of it. And what all those white marks are is as it cracked, the pavement cracks, they would go out and spray it with paint so you could see where the cracking was. This was the original pavement that we looked. We tried to find something like Ravendale. You can see the extensive cracking. We designed the mix in California and placed it in South Africa. These are the results of the overlays and the testing. This was the 75 millimeter conventional mix, the half thickness, 38 millimeters, and notice the half of the section cracked. I'll explain that in a second. This was a 25 millimeter overlay, and it looks very similar to this, as you can see. So when this was designed, I told a lot of folks at Caltrans I thought it was very conservative, the design guy we had, and they laughed at me because they said, yeah, right, it's 50% reduction, sure, and that's conservative. Well, this test and a lot of other actual projects in the field have verified that, but you can see the 3-to-1 here. This is basically what happened in the testing. The conventional section failed at 175 repetitions, and that was the design life, according to Caltrans overlay design, it predicted 172,000 net failure. Well, it was pretty close here, so we felt good about how this was going. We then went to the half section. We got up to 175,000 with no cracking. So we doubled the wheel load, no cracking, no cracking. What are we going to do now? We're running out of time. So we lowered the temperature, and after 250,000 repetitions, we got half the section to crack. So 250 compared to 175. Oops, I'm sorry. The 1-inch section, the same thing happened. We got to here, no cracking, so what we did was we doubled the load, and it completely cracked at 237. So you can see what this test shows you is that when the conventional mix is in the best condition it's going to be in, because it's going to age slower, so the thought would be that the rubber would be better later on than the conventional. The best that the conventional would be in resistance to cracking would be at the beginning. And this really validated the reduction in thickness, and it did validate that it is a very conservative approach. There was a lot of supporting research that was done at Oregon State University by Dr. Hicks, who's sitting in the audience today, and Dr. John Epps, and a number of others. Lutfi Rad did a lot of beam testing up at the University of Alaska at Fairbanks. So there was a lot of work that was done in the lab that really validated a lot of the things we were seeing in the field. This is just showing you some of the deal when you look at the wheel loads and the difference that we have with the different materials that were placed. Let's look at some projects. I want to show you some things. And a lot of this information, type information here is in my paper if you want to, that's in your books that you got. But what I want to do is I want to show you just a couple examples on how much money you can save using multi-layer strategies. The standard overlay was 135 millimeters, $337,000 was the cost. The other thing was full reconstruction, and it was $824,000. Well, this could not be overlaid because it had curb and gutter. So the only option was to reconstruct. Well, the third option was to put rubber down over a conventional thinner layer, and the cost was $263,000. The savings on this single contract was $521,000. Now, I had a guy say, well, geez, why would you use an example like the little tiny city of Hemet? And I said, well, a little tiny city of Hemet has a little tiny budget, and $500,000 on a single project is huge. Again, there was a life cycle cost analysis that was done, a very, very good research report, a number of papers has been documented over time. I'm going to tell you now about the three-layer systems and how well they can perform. Here's a project that I followed from the very beginning, and what you do is you talk about, well, this rubber looks pretty good, but this is kind of hard to believe that you're going to get any kind of life out of this. This is what it looked like. They came in and they put 25 millimeter nominal overlay leveling course on it just to level it up, put a chip seal as a SAMI, and 37 millimeters of gap-gated mix. This picture was taken in 10 years. Well, this year was the 15th year of this project, and here's a picture that was taken at the same location. There's no cracks in the entire pavement. There's a cost analysis in my paper on this project. I think it saved $52,000. Here was the other half of that project. You can see what the pavement looked like, all the alligator cracking. Here the picture is at 10 years, the same exact strategy was used. Here's a picture at 15 years. 2 years prior to this, they put a slurry seal on the top of this. It's one of the only rubber projects that I know of that they went in and actually put a slurry on. It's still performing well today. This was a project that really amazed me. You can see the wide cracks that are here. There used to be trolley cars down the center of this. The rails are still in the ground underneath the pavement. It was concrete pavement at the beginning. Here it is at 10 years old. There was only a few cracks in the pavement at 10 years. This picture was taken at 15 years. You can't see much with the shadows, so I took another one. You can see there is a little bit of cracking, and especially in the areas up here where the parking was, where you get very little traffic. But I would say that's pretty good performance for 10-year design life when we're at 15 years and it's still performing today. I'm going to kind of finish with just showing you a picture that really illustrates how well thin layers of asphalt rubber can perform. This was a section in Los Angeles. You can see the potholes here and the cracking, a lot of distress here. This is at 1 year old after we put a 25 millimeter overlay. 5 years old. Now look at the pavement around here. 10 years. There's not a single crack in the 1 inch overlay, but look at the pavement around it. It was such distress they had to come in and rehab it, and they overlaid the section after 12 years. But that really illustrates how well asphalt rubber works in thin layers on those just few pictures I just showed you. This here is one that I really like to show in the 2-layer system. The city of Ventura said, if this stuff works so good, give me a 10-year maintenance-free warranty. The contractor said, fine. He put an asphalt rubber chip seal down as a SAMI. He put a 45 millimeter overlay. This picture was taken at 10 years. There's not a crack in the entire pavement. Had no distress, no maintenance in 10 years. But this is interesting. At the time that he placed it, here is the asphalt rubber chip seal only that was placed on the pavement with no overlay. And this is what it looks like around that area now after 15 years. After 10 years. What's interesting is that if the chip seal is going to reduce the cracking for this period of time, how long do you think it's going to last with a 2-inch rubber overlay on it? Very, very, it says a lot in that single picture. So there's a lot of advantages, and you heard them today. A lot of it is that you have much higher binder contents, reduced oxidation, increased durability, resistance to reflective cracking. A lot of things with the binder you've heard earlier. But really, the biggest advantages I see today is the lower maintenance costs and the two at the bottom that are not really talked about a lot. And that is increased safety, because if you're putting down half as much material, the contractor's exposed to the traffic half the time, and the traffic's exposed to that project for half the time. And the other thing is savings in energy and natural resources. And our aggregate reserves in California are dwindling more and more each year. And this, using the reduced thickness, is a huge advantage to that problem. So that's a little history on the long-term performance of the product. Thank you very much.
Thank you very much, Jack. We have time for some questions for Jack. Time for some questions. We have a question up front. Please wait for the microphone to arrive.
Jack, are you familiar with the West End project in Sacramento?
The West End? No.
It was a rubber project on 16th Street.
When was it placed?
About a year and a half, 2 years ago.
No, I'm not familiar with it.
I was wondering about the thickness or whatever. It definitely has reduced the noise.
Oh, yes. The noise is, they were talking about noise earlier about the 8 decibel reduction, 7 decibel reduction over concrete pavement. It's at the intersection of 80 and 50 there, and that reduce, reduce, yeah. Next question?
You had mentioned on the I-80 project up in the Sierras was 21 years old before they did any rehab. What was the rehab that they did on the pavement?
It's interesting you ask. They put down, I believe they went in and put down, I'm not sure if that section was included in the cold-in-place recycling. I think it may have been. But if it wasn't included in that, they put an overlay of polymer-modified asphalt on it, which was probably 3 inches thick. I find it interesting that if you had that kind of performance for 21 years, why wouldn't you put the same thing down again? But the district chose to go a different direction. Any other questions? Yeah.
Would you recommend some kind of treatment of about 15, 20 years? In Arizona, we get a lot of oxidation, possibly a fog coat over rubber.
What kind of coat?
Maybe a fog coat.
A fog seal, you mean? Yeah, a
Yes.
fog seal. Yeah, but what's interesting is that over the course of the years of these research sections that we had, maintenance was always told, now don't do anything in this area from post-mile so-and-so to so-and-so because it's a research project by Translab. So that's one of the reasons that we don't have a lot of history on what type of preventive maintenance should we use on rubber jobs, because there really hasn't been any. And so would it be cost effective? Possibly. Some type of fog seal on it. I don't see how it could hurt. I'm not a real advocate of fog seals because they're only going to last a few years in the travel way I'm referring to.
Would you recommend any other product?
There's other types of products out there. You know, maybe something like a slurry seal. You know, in some of the projects that's a little thicker, that's going to last a little bit longer for you. Microsurfacing. We have other products in the way of seal coats that are used like on parking lots and stuff. That might be something to look at. But the fog seal is inexpensive, and it would probably do something for a few years. But because asphalt rubber ages so slowly, I don't know. After 21 years, I'm not sure oxidation was the real problem. The pavement finally just fatigued as many times as it could. But interesting question.